Okay, let's see if we can finish up this chapter. Recall we were looking at hydrolysis of acetals. If you make this acetal here, just add a little aqueous acid and run the reverse reaction and you can break it up. The question is, if hydrolysis of acetals is this reaction, but this reverse reaction is making acetals, in which direction does the equilibrium lie? The answer is whichever direction we want the equilibrium to lie. Because who do we have on our side? We have Le Chatelier, right? What would Le Chatelier do to make this reaction run to the right, to get rid of this acetal and bring it back to the ketone? Right, Le Chatelier would add a bunch of water, make sure there's a lot of water around, and this reaction will go to the right. What would Le Chatelier do to make this reaction go to the left? Well, water is a product of the reaction. Le Chatelier says if I want to make the acetal, I just get rid of this water as it forms. So we can push this reaction whichever way we want. And heck, let's use this knowledge for good instead of evil. And let's use an acetal as a protecting group. Let's look at this reaction here. You have this molecule here, has both a ketone and an ester on it, and you want to convert the ester into the alcohol. Now, good news, we know how to convert esters into alcohol. That's just lithium aluminum hydride. However, ketones are more easily reduced than esters are, which means if you took our starting molecule and just put in lithium aluminum hydride, you would reduce the ketone to the secondary alcohol and leave the ester untouched. Or if you added a bunch of lithium aluminum hydride, you might eventually reduce that ester, but then you have an OH here and an OH there. How can you oxidize this OH to the carbonyl without also oxidizing the OH you would put here? So just adding lithium aluminum hydride is not going to work. However, what we can do is protect that ketone by forming an acetal, because except for hydrolysis, acetals are fairly unreactive. So if we take our starting material with our ketone and our ester here, let's add our same ethylene glycol here with our two OHs on here, little TSOH. We know this will form this acetal. And note, we form acetals with ketones and aldehydes. You don't form acetals with esters. So we've got this acetal here, and we still have this ester over here. Note we made water. Water was one of our products. So to get this reaction to go forward, we probably would put it in like a Dean Stark trap or something that would get rid of the water. Once we have this situation, our protected ketone, our acetal, is not affected by lithium aluminum hydride. So now we can add our lithium aluminum hydride followed by water, reduce the ester to the alcohol. But now we've got to turn our protection group here. We've got to get rid of the protecting group and turn that back into the ketone. Well, that's easy. Just have Le Chatelier throw in some aqueous acid here with lots of water and push the equilibrium to form that product. Again, the product that we want. So protect the ketone or aldehyde by making an acetal. Do the reduction on the other carbonyl. Deprotect the acetal to form our ketone or aldehyde again. Okay. Well, what if we wanted a cyclic hemiacetal? Good news, we have a special name for that, a lactol. Recall that a cyclic amide is a lactam, a cyclic ester is a lactone, a cyclic hemiacetal is a lactol. So note, here's a normal hemiacetal, carbon with an OR and an OH makes a hemiacetal. Cyclic means that this R group here has to somehow connect back to this carbon. So here is our carbon with the OH, here is the OR, which connects back. So we have this ring group with the oxygen of this, well, the oxygen right here. So it kind of looks like a lactone, but instead of a carbonyl here, we have that OH. How can we make these cyclic hemiacetals? Well, let's just do an intramolecular cyclization of a hydroxyaldehyde, meaning, hey, let's just start with an aldehyde and an alcohol, but have our alcohol connected to the carbonyl carbon through a chain. So when we do this, note we're just making a hemiacetal. We have our alcohol, one equivalent of alcohol. We have our aldehyde here. It could have been a ketone. And we just add aqueous acid or base. And we get this beast right here, 94% yield. That's not, or 94% to 6% in terms of this equilibrium. That's not too bad. Something to note, two things to note. Number one, this carbonyl carbon sp2 hybridized. Now it's sp3 hybridized. It has 4 different groups coming off. It is chiral. So actually we get a racemic mixture of these two lactols. The other thing to remember is we've looked at some of these cyclic reactions before, and you might be thinking, hey, isn't this a Fischer esterification? No. Fischer esterification, we have an alcohol and a carboxylic acid. So alcohol, carboxylic acid, Fischer esterification, alcohol, aldehyde or ketone, forming a hemiacetal. Okay. But if you've made a cyclic hemiacetal, what if you want to go all the way to make the acetal from there? Actually pretty easy. We've got a hemiacetal. How did we go before from our hemiacetal to our acetal? Well, recall the hemiacetal was what we got after we added one equivalent of our alcohol to the aldehyde or ketone. Let's just throw in the second equivalent. Here we have the cyclic hemiacetal. We have our lactol here. We want to convert this to OR. Let's just throw in our second equivalent of alcohol with base, and that will put this group on that carbon. And now we have a cyclic acetal. And note it follows the same mechanism as making cyclic acetals before, from the hemiacetal to the acetal part. Something to note about these reactions. Let's look at this beast right here. Let's look at this lactol. Note we've got our cyclic hemiacetal, carbon here with the OH, OR, but note that we've got another OH down here. Look carefully. This carbon right here of the ring contains both an OH and an OR. This is a hemiacetal. This carbon here contains, well, a CH2, and an OH. This is just a normal alcohol. So we've got a hemiacetal group up here, just a regular secondary alcohol down here. Turns out that hemiacetals are more reactive than just plain old alcohols. I think one could expect that. The effect of this oxygen down here is going to affect this carbon because we've got 2 oxygens on this carbon versus just 1 oxygen on this carbon here. So if your molecule has a hemiacetal and somewhere else in there just another normal alcohol, if you react it with alcohol and H+, you will not affect the alcohol down here at all. You will just convert the hemiacetal to the acetal. I'll point it out because it should be obvious. Wait, why didn't this OH attack here? Why did we have to add this alcohol over here? Answer, because this guy can't get up there. It's bonded to this carbon. There's no amount of ring flipping is going to bring this OH up to here and form a bond there. So yeah, this OH here is kind of locked away from that carbon. Therefore, that's why we did not get any further cyclization here. You had to add a second equivalent of a different alcohol. That's not going to work. However, we have that second equivalent. You do get the acetal here, and the alcohol that started here is unaffected. At this point, you may want to look into carbohydrates. At this point, I doubt we're going to have time to get into the carbohydrate chapter in your book. So carbohydrates, sugars, starches, are essentially polyhydroxyaldehydes and ketones. Carbohydrates are one of the four main biological molecules. Carbohydrates, nucleotides, fatty acids, lipids, and proteins. So something to take a look at on your free time. We're really not going to get into this very much. If you're like, wait a minute, I want to look at all that stuff, excellent. Take biochemistry. It's a good class.